Hey folks, welcome to Chapter 5, Lesson 2. We're going to talk about friction forces and spring forces today. So we chatted about gravity last day. That was a force of attraction between any two objects. Today we're looking at friction force, which is an electromagnetic force. And it has to do, I think you guys know, friction is all about sort of one object dragging on or over top of another object. And what ends up happening, little chemistry lesson, is that the surface of all objects are covered in electrons. If you think about a nucleus with electrons buzzing around the outside. And when electrons get close to other electrons, especially if they're trying to move sideways past each other, there's going to be some repulsion. And they don't like that. It's kind of hard to actually get them to move past each other. So that's friction force. It generates a little bit of heat. It makes sliding objects over top of other objects a little bit more difficult. One weird thing about friction force, unlike gravity where the two objects are always pulling towards each other, friction force always just goes opposite of whichever direction you're trying to slide an object. So if I slide my hand over top of my desk and I'm sliding my hand forwards, friction will push backwards. And if I say, well, I'm going to go and slide my hand backwards then to go with friction, friction says, oh, no, you don't, and it'll push forwards. If I slide to the right, friction's going to push to the left. So it always opposes the motion of the thing that you're trying to slide or move. So it's kind of a bugger that way. Now, a couple of things that don't actually impact friction force. Velocity doesn't matter. So if you see a question about dragging something at a constant velocity, you won't actually need that value in there. They're just trying to throw you off. So the velocity or the speed at which you try to slide doesn't matter, and the surface area doesn't matter as well. So those two things you will find don't show up in the equation. You don't need to account for them in any sort of calculation. The two things that do matter though, and you see both of these within the equation that's coming at you in a moment here, the two things that do matter are something called the normal force. And I want to take a minute and explain what the normal force is. The normal force is the force that a surface exerts to hold something up. So you can imagine that if I took a ball and I put it on a table, I'm going to do a really terrible sketch for you here. You don't have to do this in your notes, but there's my table, and I go and I rest a basketball on the table. I have this force of gravity pulling down on the ball, and gravity's trying to pull the ball into the center of the earth. That's where gravity is the strongest, right in the core. But it turns out if I put that ball on the table, it's not going to sink into the center of the earth. And you'd say, no, Mr. Heinrich, the table's holding it up. And that's because the table is exerting a force equal to the force of gravity, because the ball's not moving up or down. And that upwards force is called the normal force. So a normal force is any kind of force that a surface exerts to just hold something up, and it counteracts gravity. So the normal force is equal to the force of gravity. 99 times out of 100. There are some special instances where those two forces aren't the same, like in an elevator. You might be able to appreciate by looking at my picture that if this were an elevator and those two forces were always the same, then the elevator wouldn't be able to go up or down, which would kind of be the world's lamest elevator. So that normal force is the same as the force of gravity. For the next bunch of lessons, we're going to make it the same. So it's the same as Fg. And remember, Fg is equal to m times g. An object's mass multiplied by 9.8, because all these things are going to be on the surface of the earth. So the normal force is technically a surface holding things up. Like if you're sitting in a chair, gravity's pulling down on you, but the chair is holding you up. So the chair is exerting a normal force on you. I put my coffee cup down on the countertop. Gravity's trying to pull the coffee cup down into the center of the earth, but the counter is pushing back with an equal and opposite force, holding that coffee cup up, just keeping it stationary. Those two forces are the same. So that's normal force. That has to do with gravity. So gravity impacts friction. The other thing is the surface type. You can probably appreciate that smoother surfaces slide past each other better. Friction is smaller. And rougher surfaces, it's harder to slide things. So that surface type gets this little symbol here, which is called mu. I like to think about that as like a French cat. That little symbol is actually like a handwritten U, kind of like that. And it is called the coefficient of friction. And it's just a number, usually a decimal, but it could be something small like 1 or 2. The coefficient of friction is just a number. There are no units, but the coefficient of friction tells you how rough the two surfaces are compared to each other. So if you're trying to slide a hockey puck on an ice rink, you might have a nice small coefficient of friction like 0.20. And then if you took that hockey puck and you tried to slide it over like concrete or asphalt, you know it's not going to slide as nicely. There's more friction because the surfaces are rougher. So the coefficient of friction might get bigger. It might go up to 0.60 or 0.70. So the bigger the value there, the rougher the two surfaces are compared to each other. And based on the normal force and the coefficient of friction, we end up with that equation right there. The force of friction is equal to the coefficient of friction multiplied by the normal force. That's what the equation looks like on your formula sheet. But remember we said that almost all the time the normal force is equal to the force of gravity. So that's the technical equation, but the sort of working version of the equation, we like to think about it like this. So the working version, you may want to add this to your formula sheet. The working version of this equation is that the force of friction is equal to the coefficient of friction, and that normal force, which is the surface pushing up, is equal to the force of gravity. So that's actually our working version, because the normal force is equal to the force of gravity. So we cheat, and I'm saying that in air quotes, we cheat and we use force of friction equals mu, the coefficient of friction, times mg. Now there are two types of friction. It turns out that when an object is not sliding compared to another surface, we call that static friction. The two things are static, they're not moving compared to each other. And there's actually more friction before the objects start to slide than once they do start sliding. Once an object actually gets going and starts sliding over top of another, we switch to something called kinetic, which means moving friction, and the force of friction actually drops. And that's why when you step on ice, if your foot isn't sliding over top of the ice, that is the maximum friction you can get. That would be static friction. And as soon as your foot starts to slide on the ice, or if your foot starts to slide, then friction actually gets smaller because now you're into kinetic friction. And that's why it's really hard to sort of like save yourself and regain your balance once you start sliding on ice, because you've actually lost some friction. Friction is decreased and you end up falling on your face. I do it every winter when I'm running home from work, at least once or twice a year. Fall on my face because I go from static friction to kinetic friction, down goes Heinrich. So let's try out an example using actually both of those types of friction and using the equation that we boxed there. So let's try this. Hopefully you can see the little subscripts. We've got a static coefficient of friction of 0.45 and a kinetic coefficient of friction of 0.32. So you can see that static coefficient of friction before we slide this dog on the toboggan. It's a little bit bigger than once we get it moving. We're going to try out two equations here. Let's figure out the force of friction, or the force required to start the sled moving. So we're going to deal with that static force of friction. So find the force. I don't know how to spell toboggan, so I'm just going to call it sled. Let's say find the force to get the sled moving. Really what I'm telling you is, hey, can I get you to go and find the static force of friction? Because we're not moving anything yet, we want to get the toboggan going. So we know, I'm going to go with that working definition of the equation, that the force of friction is equal to the coefficient of friction times the normal force. But the normal force, we cheat and we use m times g. And here we're pulling not only the dog and not only the sled, but the two of the things together. So the force of friction in this case is going to be, we're going to use the static coefficient of friction because nothing's moving yet. You can imagine the dog and the sled are stationary and we're pulling on the little arrow here, pulling on the rope. we've got 0.45 multiplied by, if you or I are pulling, we're actually pulling 20 kilograms worth of stuff. So 20 times 9.8. And let's grab a calculator here. 0.45 multiplied by 20 times 9.8. 88.2 newtons. So that's the amount of force it would take to get the sled moving, because that's the maximum that friction can fight with. That is the maximum friction force. Now, I want you to think about this. If you walked up to that dog in the toboggan and you pulled with only 40 newtons of force, what would friction fight back with? And sometimes students go, wow, the friction would fight back with 88.2 newtons. But if you think about that, if I pulled with 40 newtons, we know that the toboggan's not going to move, right? Because friction, I haven't beat friction yet. If I pull with 40 newtons and friction pulls with 88.2 newtons, that means there's more force pulling backwards with friction, and the dog in the toboggan would actually go accelerating backwards, which would be really weird. That doesn't happen, thankfully. So if I pull with 40 newtons, friction simply matches me with 40 newtons. If I pull with 60 newtons, friction simply matches me with 60 newtons. So there's this little tug of war that happens, and friction will simply match you until it can't. So I pull with 40, friction pulls against me, or fights me with 40. I pull with 60, friction fights back with 60. I pull with 90, friction fights back with 88.2, and I win. Finally, I win, and the toboggan starts to accelerate forwards. So some of you might be listening and going, well, doesn't that mean you have to pull with like 88.3 newtons then to get the toboggan moving? And the answer is yeah, but we're just going to say, hey, let's find the maximum that friction can fight with, and then we have to pull with anything bigger than that value. So let's imagine that we now did get the sled moving. Let's find the force required to keep the sled going. Required to keep the sled moving. Now remember, once the sled starts sliding over top of the snow, that the force of friction is going to drop because we end up going to kinetic friction. So this equation is going to be exactly the same as what we did in the last one. Force of friction equals, I'm going to go with the working version here, the coefficient of friction multiplied by mg. Pardon my kids' noises there if you can hear that. Here now we're into this smaller coefficient of friction. We're down to 0.32, but we're still pulling 20 kilograms of stuff times g, which is 9.8. And if we grab our calculator, now it's 62.7 newtons. So that's the amount of force required, double check that, yeah, to keep the sled moving. So I want you to think about this though. What happens if we pull with less than 62.7 newtons? So if we pulled with less than kinetic force of friction, that means friction would win out and the sled would start to slow down. It may eventually stop, but it wouldn't stop right away. It would actually decelerate. If we pull with exactly 62.7 newtons, or 62.72, whatever the number was, then we actually keep the toboggan at a constant velocity. And if we pull with more than 62.7, hopefully I got those little things in the right direction. Sorry if I got them backwards. But if we pull with more than 62.7 newtons, then what's going to happen is the sled's actually going to accelerate. So that's what that number says. It says if you want to keep the sled moving at a constant velocity, then you simply match friction. So sometimes that throws students off because they'll say, no, if you match friction, it doesn't go anywhere. No, it does. If the thing was moving already and you simply match friction, then it just stays at a constant velocity. Which means the next time you drive your car, if you put it in cruise control, the cruise control button is actually the, hey, let's match friction button. Because you know for your car, if you keep it at a constant velocity, that means you are simply matching all the sources of friction. So the friction between the tires and the road and then air resistance combined, the cruise control button says, I will exert that same amount of force forwards, and it locks it in at a constant velocity. If you take cruise control off, but you don't step on the gas pedal, now you're slowing down because friction is winning. And if you step on the gas pedal and you exert more force than friction, you start to accelerate, you're winning. All right. So let's keep going. There's one example to get us started. We'll skip all of this. I'm going to get into free body diagrams later. Let me quickly show you about elastics and springs. It turns out they work the same way. And the sort of forces that exist in them is called Hooke's Law, discovered by Captain Hook. Actually, just somebody named Hook. But great movie, if you ever saw that old one. Kind of scary, actually. The equation, don't even sketch the picture, it doesn't matter. But it turns out that when you stretch a spring or an elastic, for most of them anyways, you get a nice linear relationship where the force is proportional to how much you're stretching the spring. And the equation, we call it F with a little e for elastic, or sometimes you'll see it F with a little s for spring, doesn't matter, is equal to K times X. And in that equation, Fe is the elastic or spring force, measured in newtons. It's the amount of force stretching out the spring. X is the extension of the spring. So it's not just the length of the spring or the elastic. The extension is how much longer the spring or the elastic became. So you could almost think about extension as the growth of the spring. So if you had a spring that at rest was 1 meter long, and then you stretched it out to be 4 meters long, we'd say, oh, it grew by 3 meters. That would be your extension. So you actually look just at how much longer the spring gets than it was initially. That's your X value. And then K is the spring constant. It is just a measurement of how stiff a spring is. So let's call it the stiffness. It tells you newtons per meter, how many newtons it takes to stretch the thing out by 1 meter. So the stiffer a spring, the more force it's going to take to stretch it out, the bigger the spring constant, the bigger the number of newtons per meter. For those of you who work with resistance bands, they all have, if you buy a 3-pack and they're blue and green and red, they're all going to have different stiffnesses. That just means they have different spring constants. I know my wife has a set and they're like soft, medium, and hard or something they're labeled. But I look at that as a physicist and I just say, okay, it's 3 different spring constants and they're color-coded to make life easy. There you go. Stiffer springs have larger spring constant values. So let's try out a couple of examples. This one says how much force is needed to increase the length of a 1 meter spring to 1.34 meters if the spring constant is 430 newtons per meter. So nice straightforward question. We can go straight to our equation, Fe equals Kx. The K value, the stiffness, is 430 newtons per meter. And the extension, the extra growth of the spring when we pulled on it, it went from 1 meter to 1.34 meters. So the X value is just 0.34 meters. Throw that in your calculator. You had to exert 146 newtons in order for that to happen. Done. Let's try the second example. It's a little bit trickier. Actually, the second one's as tricky as a spring question is going to get. So we've got a bungee jumper here. We're going to find the spring constant for the bungee cord below. That dog is totally humanely harnessed. Don't worry about it. This dog is radical. We'll put him in a nice safe harness here. So let's imagine that the bungee cord, when it's just hanging there, is 28 meters long. And now we've got this dog. Maybe he's done the jump and he's bobbed up and down and he's just dangling there. So let's add that part into the story. So this dog of mass 6.4 kilograms is now just dangling on the end of the bungee cord. And the bungee cord is extended a little bit. It's now 36.5 meters. I want you to think about sort of what's going on here. We're trying to find the spring constant. And students will go to their equation. They'll say, okay, Fe equals Kx. And they go, oh, we're kind of missing two things. We're looking for K. That's the end goal, the spring constant. But we have this extra issue because we don't know what Fe is. So how the heck are you going to find this if there's two unknowns? What I want to do is actually sketch a little picture here on the side of the dog. And I'd say, well, what forces are acting on the dog? And you could say, well, the dog has mass, so there's going to be some gravity pulling down on the thing. Force of gravity equals m times g. That's great. And that's not the only force acting on the dog, thankfully. Because if that were the only force on the dog, then the dog would be accelerating down towards the surface of the earth, and that might not be a good thing. I'd say, well, okay, the dog's dangling there. Gravity's pulling down. What's holding the dog up? And you'd say, well, the bungee cord is. All right, so there is this spring or elastic force that's holding the dog up. And we know Fe is equal to Kx. And if the dog is just dangling, not accelerating up, not accelerating down, what can you tell me about those two forces? Well, if the dog's not going anywhere, don't those two forces have to be the same? And that's key here, right? Is that those two forces are actually equal because the dog's not moving up or down. So what we can do is we can modify our equation a little bit. We can say Fe is equal to Kx. Well, in this special case, Fe is equal to Fg. Those two forces are the same. And then what I'm going to do is I'm going to expand each one of those equations. I know that Fe is equal to K times X. And I know that Fg is equal to m times g. And now we've actually got enough information that we can solve for that K. Because it turns out that's the only thing we don't know. So if we go and we plug numbers in, it's K times, remember X is your extension, it's the extra length of the spring. We've gone from, I'll just show the subtraction, 36.5 minus 28 equals, the dog is 6.4 kilograms times 9.8. And if you go and you run those numbers in your calculator, I'm just going to do it off the screen here. Oh, what the heck, I'll do it right on the screen. I might as well show you. What have we got? 6.4 times 9.8 divided by 36.5. Notice I'm using brackets so I don't run into a bed mass issue. 36.5 minus 28. We get a spring constant of, what, call it 7.4. 7.4 newtons per meter. So that's the stiffness of that bungee cord. So that's a bit of a special case, something dangling on the end of a spring or an elastic. You know that elastic force is the same as the force of gravity. So that is lesson number 2. The homework that goes with this lesson is worksheet number 2, which you'll find in the All Resources folder. So give that worksheet a try. Remember that you probably will get stuck on some of those questions. If you do, hit me up with an email or join me for a Zoom meeting. There is some gravity stuff on that worksheet, just so you're not surprised. There's a little bit of review just mixed in there. But I hope to chat with you soon to answer some questions about this, because you're going to have some. We'll figure them out together. Until then, take care.